It is one of the preeminent nuclear science and engineering programs in the world. The Massachusetts Institute of Technology is home to cutting-edge research and some of the most brilliant minds in the fields of fission, fusion, and nuclear science and technology. Among the oldest graduate programs of its kind in the U.S., NSE alumni have been at the forefront of nearly every advance in nuclear technology in the past 50 years. NSE was officially founded as the Department of Nuclear Engineering on July 1, 1958. But nuclear research began somewhat covertly at MIT years before that.
MIT had this secret project for a research reactor in the late 40s on which I worked. I wasn't supposed to talk to anybody about it. Another fellow who was a couple of years older than I in the PhD program in chemical engineering was also on it. And as I say, we took data. It was just merely airflow, and we had to measure pressures.
Nuclear was a burgeoning field, so MIT went straight to the Manhattan Project to recruit the top nuclear minds. They found a chemist named Manson Benedict, who would soon be known as the founding father of nuclear studies at MIT.
Professor Benedict was very well known because he was a major contributor to processing uranium and extracting the proper isotope for the building of power reactors.
He was very soft-spoken, very, very intelligent, a good organizer, and a motivator in a very quiet way.
Culturally, in terms of collegial conduct and so on, he set a very high standard for us. So oftentimes, we say to ourselves, we're a friendly department because Manson started this way.
While Manson was department head, the whole department, graduate students and faculty, would go out to his house in Weston and have a steak fry. And there was an open field nearby where we'd play touch football, and that would get the students and the faculty together, and he encouraged that.
Well, he was, I guess, the ultimate father figure for us all.
In 1948, the U.S. Navy was focused on developing nuclear energy to power its submarines. Admiral Hyman Rickover was named to head the project. Nearly half of his first recruits came directly from MIT.
He wanted to establish somewhere he could get trained people in a discipline which then didn't exist. So he was trying to encourage MIT to do it, and I suspect that when he discovered he had 7 out of his first 16 people came from MIT, it may have occurred to him, well, maybe they're doing something good up there.
And Admiral Rickover did so with his own special brand of military might.
There are lots of stories about he would intimidate candidates. He would have his chair elevated on blocks, so he looked down, and then he would cut off, reduce the height of the front legs of the chair, so the poor candidate was leaning forward all the time. And so this is the way he tested them to see whether they could really stand up to the rigors of the nuclear navy. Once he called Manson at 11 o'clock at night and said, "I'm going to be up in Cambridge at 3 o'clock in the morning. I want you to be at MIT to meet me." And Manson said, "I don't go to MIT at 3 o'clock in the morning." So he kept the admiral waiting.
By 1950, the Institute decided to focus instruction and research in nuclear engineering within one department. Named Course 22, the curriculum was still being developed, and that created challenges for students and instructors alike.
Manson said, "I had to teach nuclear reactor physics too." And I said, "Gee, I haven't even taught or ever had a course in nuclear reactor physics 1. So that very much accelerated my own self-education. All through my career in nuclear engineering, I had to stay a week ahead of the graduate students by developing this material. You can't wing it in front of MIT graduate students.
I heard that there was a professor in chemical engineering who was giving a survey course about nuclear power. At the time, he tried to cover, by design, everything about nuclear energy and nuclear power in one semester. And I had the audacity to sit down and write a letter to the head of the department. I wrote that I'm puzzled that the most important aspect of nuclear power is covered at MIT in 10 minutes. I had also the audacity, out of ignorance, to write an outline of what the subject should contain. 2 weeks after I sent the letter, I received one from him, which in his nice way of speaking to students says, "Elias, get ready. Next term you start teaching the course you recommended." And that's how I started teaching nuclear engineering.
In 1955, MIT expanded its program to offer a doctorate degree in nuclear engineering. School officials also made the important decision to build a first-class university research reactor. Theos Tommy Thompson joined the faculty from Los Alamos National Laboratory to take charge of the project.
Tommy was somewhat different than Manson. He was a driver and also a very intelligent man. He had to in order to get this thing built and get the land, get it licensed.
MITR-1 went live 3 years later in July of 1958.
At first, there wasn't quite enough extra fuel to bring it up to power. It would go critical, but it was at low power, so we had to wait a while until more fuel was built, and then research programs really began to develop. Gordon Brownell had helped in design the reactor so that there was a room right below it, and there would be a window through which neutrons could be taken to do cancer radiations.
Despite a growing anti-nuclear movement in the country, the Cambridge community had little to say about its nuclear neighbor.
There was excitement within the institute because this was a new tool for fundamental studies about nuclear power plants, their characteristics, their methods of control. At the time, the people were not objective to nuclear power like they have been in recent decades.
The reactor has always had a very, I would say, comfortable relationship with the city of Cambridge. I think MIT has been very responsible. They've included the Cambridge city leaders and services in their analysis of the safety and security of the reactor. So far, I think it's been a very good relationship.
It's run by students. They become licensed operators by the NRC. So it's a whole other experience that you won't get at most other universities.
With interest in nuclear studies growing at a fast pace, MIT decided to separate Course 22 from chemical engineering and establish the Department of Nuclear Engineering. Manson Benedict was the obvious choice to head the department.
Manson was a guy who led by example. He was always very factual, very straightforward, very warm in a formal sense, but you knew he was very much involved, interested in the student well-being.
Over the next 5 years, the department brought on several new faculty members and doubled the number of subjects. MIT was on its way to becoming the preeminent place for nuclear studies in the U.S. The work was hard, the subjects serious, but some faculty members still managed to find time for fun.
Norm Rasmussen used to like to play table tennis with the students at lunch hour. Every day, he would just jump up and go to the 3rd floor where the table tennis was in the student lounge and have a few games there.
That was very much his personality. He enjoyed students very much, and he enjoyed a good joke.
Well, I remember the one they did on him, and his office was over in the reactor building, and the fellow who ran the machine shop was Woody, and he and Norm always had a rivalry.
The guys in the shop said they would buy him a turkey. He said, "Oh, that's great." So he came back to his office, opened it up, and there was a live turkey walking around in his office.
So he expected a dressed turkey. He got a live turkey, and his office, since the turkey was there for quite a while, turned out to be quite a mess. So that was a surprise on him.
Norm Rasmussen's contributions to the department went well beyond humor.
Norm was one of the early hires in the department, and when he was hired, he was a specialist in radiation measurements, and in particular gamma ray spectroscopy.
Professor Rasmussen had this idea of putting things in perspective, using risk. Nuclear power has certain risks associated with it, but there are other things that we do technologically that are much more risky. And he tried to make this contrast between nuclear power and, say, driving a car, flying an airplane, man-made, and natural disasters.
When the Nuclear Regulatory Commission wanted to apply this probabilistic approach to assessment of the safety of nuclear reactors versus other industrial activities, it was natural for the department to suggest that Norm should be the MIT professor to lead that effort.
Rasmussen's 1975 reactor safety study received worldwide attention and became one of the most influential elements in nuclear safety and licensing. Dubbed the Rasmussen Report, many of the methods it introduced are still in use today.
That was a landmark in the history of reactor safety assessment.
Another NSE professor doing landmark work at MIT was Alan Henry. Once the head of reactor theory and methods at Bettis National Labs, Henry developed mathematical models to describe neutron behaviors in reactors.
He was really creating the technology that exists today on nodal methods in physics. I knew through interacting with a lot of students how much his students respected him and how well they enjoyed working with him.
The department expanded from fission to fusion in 1958 with the appointment of MIT physicist David Rose.
He really began the fusion program, and he, with a man named Melville Clark, wrote a very well-known book, textbook actually, on fusion and plasma physics. Turns out that the book is still extremely current. The topics are still those that are taught in our introductory course, and the level is really quite sophisticated for a book that's written almost 50 years ago.
He was really a pioneer, way ahead of his times. And the most important thing that I can remember him saying and teaching, and I took a fusion course from him, was the interconnectedness of things. In other words, you can't just operate in isolation of what else is going on in the world, not only from the reactors, but also from their impact on society and other influences.
He broadened his interests into energy.
He was way ahead of the curve in a way in looking at the problem of energy supply and how we're going to ultimately provide energy for the world. And one of the most famous students was Larry Litsky, who also joined the department, I believe, in 1962.
He was originally one of the promoters of the pebble bed reactor, which is something I rejected when I was vice president of Yankee Atomic, because I didn't think it was a needed technology. We had very good light water reactors. They were functioning well, and from the utility perspective, we just didn't see the need to go into this new direction. Well, as irony has it, I am now one of the biggest promoters of this technology.
Tom Dupree taught a course in plasma theory, which I took as a graduate student along with friends of mine. He was a very inspirational teacher. It was, at the time, the most advanced ideas in plasma, what's called now plasma kinetic theory. And Tom went on to make seminal contributions in the theory of plasma turbulence, a very important area for plasma physics today. Jeff Friedberg was a scientist working at Los Alamos. He was an outstanding theorist and researcher. But more than that, he brought with him a reputation, I suppose you'd say, as an outstanding plasma theorist in the area of magnetohydrodynamics, which was a new area for us at MIT, because nobody had been exploring that area in any depth at the time.
During the 1970s, NSE increased its curriculum and began offering a full undergraduate program. Major reconstruction of the reactor was also underway. The redesigned reactor, called MITR-2, had a more compact core and was cooled by light water. Another major development was a plasma experiment, a fusion reactor, which became known as Alcator.
And it was actually brought to MIT by Bruno Coppi. He came here from Princeton to MIT, and he had the idea of wanting to build a large-scale fusion device.
That project was very ambitious, very high magnetic field, drawing on the skills of the Magnet Lab and of Bruce Montgomery and the people there.
My memory of the first days of designing the machine was sitting around a table with perhaps 8 or 10 people, Larry Litsky, I remember, Bruno, of course, and others. And I felt like we were all a bit like the blind man filling the elephant, and we all had a different idea of what this might look like. And none of us really knew, in the end, what we were in for until we had done it. So that allowed us to go from plasma temperatures from a few electron volts to 1,000 or several thousand electron volts. So that was a huge step.
Alcator paved the way for MIT's involvement in a global experiment with fusion energy, the International Thermonuclear Experimental Reactor, better known as ITER.
ITER would be the world's first real fusion reactor. That means the first device that would actually produce net fusion power, more fusion power out than power in.
MIT is at the forefront of this 7-nation collaboration, a worldwide experiment in fusion with the potential to produce near limitless power with minimal risk and without radioactive waste.
Maybe we could think of it in terms of airplanes, and going back, perhaps ITER would be the Wright brothers' step of actually showing that manned flight is possible. And in the same sense, ITER would show that fusion is possible. So it's a tremendous step toward realizing fusion energy, and something we've never been able to take before.
Alcator A was followed by even more powerful tokamaks, Alcator C and Alcator C Mod, the largest university-run fusion reactor in the world, and one of only 3 in the United States.
The Alcator CMOD tokamak is directly addressing the challenges that the ITER, International Thermonuclear Experimental Reactor, will face. And since that program is now going forward in the south of France, and we are involved in it, students who come to MIT have the opportunity to get involved in that 7-nation program.
While the bulk of nuclear research at MIT has focused on using nuclear power to create energy, some of the Institute's most renowned work has been on nuclear engineering's other functions.
Well, medical and other diagnostic applications of nuclear and radiation interactions have long been a part of what this department has been doing. And so, for example, Gordon Brownell, who was for many years a professor in our department, was one of the founders of so-called the PET scanning.
Brownell's work with Mass General Hospital in the early 1950s led to the first use of nuclear radiation to diagnose brain tumors. His pioneering research is helping doctors more accurately treat cancer patients today.
Predominantly, proton therapy is valuable because it enables us to deliver radiation very locally to an area of a person's physiology where there might be, for example, a tumor that we want to kill.
And Brownell's influence on nuclear medicine led to developments in functional magnetic resonance imaging techniques which are used in hospitals throughout the world.
So I think that there'd be many, many people in the world would not have survived had it not been for the use of radiation.
There's been excellent work done at MIT in the area of boron neutron capture therapy, led by Otto Harling and Jeff Coder, that has been really world-leading because of the excellent fission converter that was designed and built here.
MIT researchers like Richard Lanza are also developing technology that will use neutron and X-ray imaging to scan luggage and detect explosives, a uniquely 21st century application.
This is very important, of course, at the moment for homeland security, and again, we bring our nuclear techniques to bear upon this.
NSE professors are working together to leverage their knowledge and experience. Sidney Yip and Xiaoxin Chen's collaborations have broken new ground in spectroscopy.
So Sidney is an expert in the molecular dynamics and in the theory, but Xiaoxin is an expert in designing experiments to elicit what happened microscopically. And so early they could collaborate.
And quantum computing, the next frontier in computer technology, has found a home at NSE through the work of radiation science and technology researchers like David Corey, who is using nuclear magnetic resonance to probe more deeply into materials.
He's basically started a whole new field with his NMR approach.
We can build memory based upon quantum mechanics that would be more efficient. We can make gyroscopes that are more precise. We can make time standards that are more precise. And so it's easy to imagine that. But there are broader applications that are going to transform the world.
For students getting involved in the nuclear science and engineering today is probably the best time for nuclear, because it's at the beginning of what we call the Renaissance.
The whole attitude towards nuclear power is changing in this country. People are realizing the importance of global climate change, and that nuclear is one of the absolute key ways of addressing this. I would say we, as a department, believe very strongly in the future of fission power, and perhaps in the longer-term future in fusion as being a vitally important way in which the department can contribute to society's needs.
The demand for young engineers is enormous. So we have a big job to do here at MIT to attract students to the department.
The quality of the professors and the research that they do really drew me here, and I've been extremely satisfied with how that's turned out. Actually, I've worked with top-rate people. You can kind of, write out equations or, do some mental studies, but until you actually really see what's going on, it really reinforces all the concepts that they teach you in the classroom.
I'd wanted to go ever since I was a little kid to MIT. It was my top choice. It's a group of people who are willing to take the next steps and build the next project and do the next steps in the research. So there's always going to be something going on. And it's a great learning experience.
I hope we will attract bright students that will not only learn what we know up to now, but they will come up with new ideas which might make nuclear power even better and more acceptable.
In 50 years from now, nuclear will be at 250 graduate students and will be providing education for an equal number of undergraduates as graduates, since we will have at least 50% of our energy being produced from nuclear means.
I hope the department will continue its efforts to educate the public on the peaceful uses of nuclear energy and the safe uses, and be able to train a new generation of people that can develop and design and build and operate nuclear plants safely.
The way that I think that the department can evolve is to try to take advantage of experience and insight from the past and connect that with younger people who are looking forward to the future.
I'm hoping that we'll have a community of students that will get together and form the first generation of companies to make quantum information devices.
We hope that the next generation nuclear power plant will in the near future begin to move forward and probably to be sited at INL, and we intend to be a part of that activity. Of course, it's going to be the new generation that will do that, and that's what makes it terrifically exciting for students.
If you have a passion and a vision for what you'd like to do as a nuclear scientist or nuclear engineer, this is the place. We're internationally recognized as the #1 school in nuclear science and engineering, and we have faculty who are world-renowned, and it's an exciting place to be.